All right. Conceptually, we have a really dense question. To anybody who's studied special relativity or general relativity, you're definitely aware of what's about to happen and how to draw these out. But it's a long question, so I'm just going to dive in and we'll just have a discussion. This one in particular, I think we should have a good discussion in the comment section. Because I really think that this is a really cool thing, and we will have to see it again in other classes and in the last chapter. So let's go ahead and dive in. So the statement is, I showed that at most one point on the particle's trajectory communicates with R at any given time. And in some cases, there may be no such points. An observer at R would not see the particle in the colorful language of general relativity. It is, quote, over the horizon. As an example, consider a particle in hyperbolic motion along the x-axis. Here, that's defined as Wt is equal to square root b squared plus ct squared in the x-hat direction for t between negative infinity and infinity. That's a typo as well, excuse me. In special relativity, this is the trajectory of a particle subject to the constant force F equal mc squared over b. Okay, that kind of looks like the radial part where we have v squared over c or v squared over r, something like that. But nonetheless, let's continue on. What we want to do is sketch the graph of W versus T. At 4 or 5 representative points on the curve, draw the trajectory of a light signal emitted by the particle at that point, both in the x direction and in the minus x direction. What region on your graph corresponds to points and times x, t, for which the particle cannot be seen? At what time does someone at point X first see the particle? Prior to this, the potential at X is 0. Is it possible for a particle, once seen, to disappear from view? Ooh, we got some fun stuff, but man, this is going to be a headache. You have to be very, very careful. So, the solution starts with a person at point X sees the particle when this point is reached, i.e. at x equal negative ct, or t equal negative x over c. So let's draw it out. Let's see what we're dealing with. Okay. So if we have w of t, and then we have the x-axis here, where we see x equal negative ct, that curved squiggly line, or the wavy line, is the region below the wavy line represents space-time points for which the particle is invisible. Okay, when it's moving, again, it has to happen at the retarded time, and that retarded time has a delay. That delay is the negative ct that we're looking at. So if we graph w of t with respect to t, what we see here is that we get a hyperbolic motion, so it looks kind of like a parabola except more spread out. And we choose light rays in the positive x direction, okay, here alongside the graph of Wt. So if we look at A, we get a positive and negative, okay, it reflects off perpendicularly, B perpendicular, C perpendicular, D perpendicular, and then down the x, down, separated by distance B is the focal point or the loci of the hyperbola. And what we need to surmise here is that the light rays in the negative x direction form particles at points A, B, C, and D. Okay, this is so if we're tracking down the A path, if we're tracking down WT at A, boom, then we see it. C or B, boom, then we see it. C, we see it. D, we see it. If we were behind that x equal negative c line, we would not be able to see it. This is, we've seen like the horizon, so to speak, from general relativity, or the cone, the light cone. This is coming through the same way. This is a much, I believe this treatment needs a much more handling than what we can see in this particular aspect, and maybe I need more experience myself, but I think it's safe to assume that everything that we're about to encounter in our studies is going to be predicated on understanding how this setup works. So it is definitely worth understanding and learning about.